An airline chatbot invented a policy that didn't exist. A professional government report contained citations to sources that weren't real. And in both cases, the AI didn't sound confused. It didn't hesitate. It sounded completely certain. That is the part of AI hallucinations most people misunderstand. The danger isn't simply that AI can be wrong. Humans are wrong too. The danger is that a false answer and a correct answer can arrive in almost exactly the same confident, polished voice. So how do you know the difference? By the end of this video, you'll understand why hallucinations happen, where they become most dangerous, why reasoning and RAG don't completely eliminate them, and how to verify AI output before you trust it. I'm Kaushik, and this is Tech with Kaushik, where we simplify AI, cut through the hype, and show you what it actually means in the real world. And today, we're meeting the world's most convincing improviser. Here's a real example. In 2022, after the death of a family member, a passenger used Air Canada's website chatbot to ask about bereavement fares. The chatbot told him that he could apply for the reduced fare after traveling, so he relied on that information. Air Canada later denied the request because its actual policy did not allow the fare to be claimed retroactively. The dispute eventually went to British Columbia's Civil Resolution Tribunal, and in 2024, the tribunal held Air Canada responsible for the inaccurate information provided through its own chatbot. The financial award itself wasn't enormous. The principle was, a company couldn't simply say, "The chatbot said it, not us." Once AI output affects a real decision, hallucination stops being an interesting technical flaw. It becomes a real-world liability. Now move from customer service to professional consulting. Deloitte prepared an assurance report for an Australian government department. The contract was worth roughly 439,000 Australian dollars. But after publication, researchers identified problems in the report, including incorrect references and citations to material that did not exist. A corrected version was later published, and the report disclosed the use of Azure OpenAI technology. Deloitte also agreed to a partial refund of the contract. But here's the important lesson. The failure wasn't simply, someone used AI. The failure was, AI-generated material reached a consequential document without sufficient verification. That's the distinction we'll come back to throughout this video. So what exactly is happening? First, we need to remove one misleading idea. When an AI hallucinates, it isn't necessarily lying. Lying implies that you know something is false and intentionally tell someone the opposite. That's not a useful model for what's happening inside an LLM. And I wouldn't say the model literally believes its false answer either. Instead, something stranger happens. The system generates a sequence of words that fits the patterns it has learned, and that sequence can be completely wrong. But the language can still be fluent, specific, professional, authoritative. The key insight is, confidence in the writing is not evidence of confidence in the truth. Fluency and factual reliability are two different things. Here's the metaphor I find most useful. Imagine an extraordinary improv actor on a stage. You give them a situation, and their job is to continue the scene. No script, no time to search a database, no fact-checker standing beside them. They listen to what came before, predict what would make sense next, and continue. If the scene is about a doctor, they sound like a doctor. If it's about history, they tell a history story. If it's about law, they can produce something that sounds legal. Obviously, an LLM is not literally an actor, and nobody simply programmed every language model with the instruction, "Never say, I don't know." But as a metaphor for why plausible continuation can become plausible fiction, the improv actor is surprisingly powerful. Look at the rule on the wall, never break character. Keep the scene going. Again, think of that as a metaphor. Language models learn statistical patterns from enormous amounts of text. During generation, the model repeatedly predicts what token should come next, then the next, then the next. Usually, that's incredibly useful. But imagine asking for a fact that isn't well represented in what the model has learned, or asking for a citation that doesn't exist. The model still has something it is extremely good at doing, continuing the pattern. A realistic author name, a plausible journal title, a believable court citation, a confident explanation. The sentence can become more convincing, even while the factual foundation becomes weaker. Now imagine the actor performing again and again. Whenever the answer is correct, applause. But here's the interesting part. Suppose the actor isn't sure. If they refuse to answer, they get no point. If they guess, they might get the point. What behavior does that scoring system encourage? Guessing. That is closely related to a problem researchers have identified in language model evaluation. Many traditional accuracy benchmarks reward a correct answer, but don't sufficiently reward a model for recognizing, I don't know. Under that scoring system, a guess can be strategically better than abstaining. So the problem isn't simply that a model has learned to sound confident. The deeper issue is that some evaluation systems make guessing economically rational in score terms. Now the actor finishes the performance. The audience erupts. Everyone is rewarding the answer. But in the front row, one person is holding a sign. That's false. That's the failure we care about. A system can look impressive on one dimension, while being poorly calibrated on another. It can produce an answer that humans prefer because it's complete, clear, and decisive, without communicating enough uncertainty about whether the underlying claim is true. So if we want more trustworthy AI, accuracy alone isn't enough. We also need something called calibration. When the model is uncertain, does its behavior reflect that uncertainty? Can it abstain? Can it tell us when verification is needed? That's a very different objective from simply producing an answer. And this is where the metaphor meets actual research. In 2025, OpenAI published work examining why hallucinations remain so persistent. One of its central arguments was that common training and evaluation procedures can reward guessing over acknowledging uncertainty. In other words, our measurement systems can unintentionally create the wrong incentive. That does not mean every AI company deliberately trained models to bluff. And it doesn't mean confidence is a single switch hidden somewhere inside the network. The point is subtler. If we score systems mainly on whether they produce the correct answer, without properly rewarding, but a hallucination doesn't always end with one conversation. Imagine an AI generates a false claim. Someone publishes it. Another website copies it. A summary repeats it. Another AI system retrieves that page later. Now the false statement can begin to look less like an invention and more like something that has been repeated in multiple places. That does not mean every new model blindly treats every old AI output as truth. Modern training pipelines use filtering, curation, and many other controls. But the broader feedback loop risk, researchers call one version of this problem model collapse. Experiments have shown that if successive generative models are trained indiscriminately on recursively generated synthetic data, important parts of the original data distribution can gradually disappear. Rare information can be lost. Distortions can accumulate. The model's representation of reality can become narrower over generations. But here's an important caveat. This does not mean model collapse is inevitable. Other research shows that retaining high-quality real data and carefully managing synthetic data can substantially change the outcome. So the lesson isn't, AI will poison the internet and collapse automatically. The lesson is, data provenance and data quality matter more as synthetic content grows. And if you like this kind of explanation, where we separate the dramatic headline from what the research actually says, give the video a like and subscribe to TechWithKoushik. Because now the story gets even stranger. This image shows our actor completely convinced by the script. But this is where the metaphor reaches its limit. An LLM doesn't need to literally believe its own story. It doesn't need a human feeling of certainty. The danger is more mechanical than that. The model can generate a false premise, then generate the next sentence consistent with that premise, then the next and the next. Each continuation can make the original mistake feel more coherent. So what looks like doubling down from the outside may simply be generation remaining consistent with earlier generated tokens. That's why asking, "Are you sure?" is not a reliable fact-checking system. The same model may confidently verify its own mistake. Then reasoning models change the conversation. Instead of immediately producing the final answer, these systems can spend additional computation working through a problem before responding. And on many difficult tasks, especially mathematics, coding, and structured reasoning, that can improve performance substantially. From the outside, it can look like the model is finally showing us how it thinks. Step 1. Step 2. Check this. Reconsider that. Arrive at the answer. But there's an important distinction. A visible reasoning trace can be useful, without necessarily being a perfect transcript of every internal computation that caused the answer. And researchers have started testing exactly that. Researchers use the word faithfulness for this question. Does the reasoning the model shows us faithfully reflect what actually influenced its answer? In experiments with reasoning models, researchers have inserted hints into prompts, then checked whether the model used those hints. Sometimes it clearly did, but its visible chain of thought failed to mention them. That matters, because it means the reasoning trace can be informative without being a forensic recording of everything happening inside the system. So don't make either extreme mistake. Don't say, chain of thought is fake. And don't say, chain of thought lets us read the model's mind. The evidence suggests something more interesting. It can reveal useful reasoning, but it is not always faithful. Then DeepSeek, R1-0 added another twist. R1-0 used large-scale reinforcement learning without supervised fine-tuning as the preliminary post-training step. And during reinforcement learning, increasingly sophisticated reasoning behaviors emerged. The model began producing long reasoning trajectories, breaking problems into parts, reconsidering intermediate results, and showing behaviors researchers described as emerging through reinforcement learning. That's remarkable, but be careful with the conclusion. It does not prove that the model is conscious. It does not prove that no step-by-step reasoning patterns existed anywhere in its pre-training data. And it doesn't magically settle what real reasoning means. What it does show is that sophisticated reasoning-like behavior can emerge from optimization in ways that are more complicated than simply copying a human-written chain of thought template. And that brings us to one of the most interesting debates in modern AI. One side argues that today's language models are fundamentally sophisticated next token predictors, and that their impressive behavior should not be confused with the flexible world model-based reasoning humans perform. Researchers such as Jan LeCun have strongly emphasized limitations of current autoregressive language models. On the other side, we have systems solving difficult mathematical problems, writing complex software, planning, playing games, and exhibiting reasoning behaviors that were not explicitly hand-programmed. So which side is right? Part of the disagreement is about what we mean by the word reasoning. And I don't think you need to settle that philosophical debate to use AI responsibly. Because operationally, there's a simpler question. How robust is the reasoning when the problem changes? And that's where current systems still reveal brittleness. A model can perform brilliantly on one formulation of a problem, then make a surprising mistake when the assumptions, wording, or structure change. It can succeed on a familiar pattern and fail on a nearby variation. That doesn't prove that there is no reasoning, but it tells us something important. High benchmark performance is not the same thing as reliable general reasoning under every distribution shift. So when you're using AI on a genuinely novel problem, one with unusual constraints, or one where no obvious precedent exists, your verification threshold should go up, not down. The more novel the task, the less you should let fluency substitute for evidence. So where should your hallucination alarm be strongest? Here are the danger zones. Open-ended factual questions where you haven't supplied sources. Citations, papers, court cases and references. Recent or niche information. Legal, medical, and financial specifics, where a small factual error can matter enormously. Novel combinations that require the model to generalize beyond familiar patterns. And highly specialized terminology where the model may know just enough to sound convincing. Lower risk uses include creative brainstorming, rewriting text you've already supplied, extracting information from a provided document, or generating code that you can actually run and test. Notice the pattern. The safest tasks give you an external way to check the output. Quick question for you. What do you personally verify most often from AI? Facts, citations, code, or something else? Put just one answer in the comments. I'm curious which failure mode people encounter most. Now remember RAG, Retrieval Augmented Generation. RAG can reduce a major source of hallucination by retrieving relevant evidence and placing it in the model's context before generation. Instead of relying only on what the model learned during training, you give it documents it can use right now. That's powerful. But RAG is not a truth machine. Retrieval can bring back the wrong document. The source itself can be outdated. Relevant evidence can be missed. The model can misunderstand what it retrieved. or it can still generate a claim that isn't actually supported by the source. So I would phrase it this way. RAG improves grounding. It does not guarantee correctness. Grounding is one layer of reliability. Verification is another. Now put the same problem inside a multi-agent system. Suppose one orchestrator generates a false assumption and passes it to 5 worker agents. If every worker treats that statement as trusted context, one hallucination can become 5 coordinated mistakes. Then those outputs may feed into another report, decision, or action. That's the cascade this image represents. But again, architecture cuts both ways. Multiple agents can also be designed to challenge, verify, or independently check one another. So multi-agent systems don't automatically amplify hallucinations. They amplify whatever trust structure you design. If agents blindly inherit upstream claims, errors propagate. If critical claims require independent evidence, the same architecture can become part of the defense. So what should you actually do? Use this 3-layer framework. Layer 1, recognize. Ask, is this factual? High stakes? Recent? Niche? Citation heavy? Novel? If yes, assume the verification burden is high. Layer 2, verify. Don't just ask the same AI. Are you sure? Go to evidence. Open the citation. Check whether the paper exists. Read the relevant passage. Use an authoritative source. For code, run it. For mathematics, independently calculate it. For data, inspect the original dataset. A second model can be a useful cross-check, but agreement between 2 AIs is not proof. And finally, Layer 3, trust. Trust the output only to the degree that the supporting evidence deserves. That isn't paranoia. That's AI literacy. So think back to our actor. At the beginning of this video, the performance was so convincing that the audience forgot to ask whether the script was true. Now you know what to look for. MCP can give AI access to tools. Agents can give AI the ability to act. Multi-agent systems can scale those actions. RAG can give AI access to relevant knowledge. Reasoning can make AI dramatically more capable. But none of those capabilities removes one fundamental responsibility. Important claims still need evidence. The mature AI user doesn't ask, does this answer sound intelligent? They ask, what supports it? Because confidence is presentation. Evidence is verification. If you want to see how grounding works in practice, watch my RAG explain video next. Because that's one of the most important tools we currently have for reducing unsupported answers in real AI systems. And subscribe to TechWithKoushik if you want more practical, research-backed explanations of how AI actually works. I'm Koushik. Thanks for watching, and I'll see you in the next one.